Next speaker is Ravi Montenegro from University of Massachusetts Lowell, and he'll tell us about two seemingly very different things and how they're related, the birthday paradox and the discrete logarithm problem.
Okay, so this is work with three other authors, as you see there, three of whom are of us who are here today. So I'll start by talking about the discrete logarithm problem as a motivation for what we'll be studying later, which is a Markov chain. So the discrete logarithm problem is of interest, among other reasons, because it's related to the Elgamal encryption scheme. A very simplified version of how this works is that we have Alice and Bob, and Alice picks a cyclic group of, say, prime order, and picks a random exponent x, and the public key that she tells everyone will be the group, a generator, the order of the group, and then the generator to the power of x, where x is the private key. And then Bob can send a message using that. He picks his own random exponent. He encodes his message in the group and sends two group elements back. And then Alice can read the message by the following computation. So we can see that if an outsider could intercept the information that was sent back and forth and find the missing exponent x, then they would be able to read the message as well. And so this is our discrete logarithm problem. We have a generator of a cyclic group of prime order. We have another element h, and we want to find what the exponent is, x, in order to get the element h out. So Pollard suggested a method for solving this. The Pollard Rho algorithm for factoring is a bit more well known, but there's also one for discrete logarithm here, and the principle is fairly similar. Roughly speaking, we pick ordered pairs of elements at random and compute the generator g to the first term times the h, whose discrete log we want, to the second term. And if we do this a whole bunch of times, since our group has finite order, eventually the same term will come out twice. And once that happens, since h was g to the x power, we can rearrange terms and find what x is most of the time. Occasionally you'll have bad luck and you'll get some degenerate situation. So the birthday paradox tells us that if we were picking these random exponents a and b for about order root g times, then eventually we would have this equality occurring and potentially be able to find the discrete logarithm. Okay, so there's an obvious problem here. If we were actually to check the computation there for every outcome we get, we would have to take about 1.25 root g or choose two comparisons, and that wouldn't help us at all. So the way that's gotten around is by using this method called Floyd cycle finding algorithm. And basically we add a deterministic bit to it. So we choose a function at random and fix it, and then the new sets a comma b that we're going to be working with will just be the output of that function given the previous input. And the point is that if we set this up right, after a while you'll find that once this collision occurs, if you go a little bit longer, it'll be good enough to be comparing the ith terms. I wrote that wrong. That should be g to the ai times h to the bi should equal the second term there eventually. So we don't have to compare every pair. We just have to compute the ith thing chosen at random and the two ith one. So then what Pollard's algorithm really is that we partition our group into three pieces, and the particular random function we'll be choosing will be either increment the first term, increment the second term, or double both of them. And that's based on whether or not the group element we're getting here is in the first, second, or third partition. Teske found by just doing a bunch of simulations that this takes about 1.6 root order g steps in order to get a collision and possibly find the discrete logarithm. So that compares to the birthday paradox, which says about 1 1/4 should suffice. So it seems that at least if we're starting from random states, then it's not much worse than what the birthday paradox would have predicted. But it would be nice if we can prove something rigorous. And the way this is going to be done is by making an observation of how this can be related to a Markov chain. So if the partitions that we chose were random in the sense that every element of the group was assigned to one of the three partitions with equal probabilities, then effectively the first time that you visit a state, you're making a random choice on what you do on the next step. With probability 1/3, you increment the first coordinate, probability 1/3, you increment the second, and probability 1/3, you double both of the coordinates. So now we have a Markov chain, and our question has to do with how long it takes for the Markov chain to return to a state that it's visited previously. So there are a few results about this discrete logarithm problem. First of all, Pollard-Hellman showed that it's good enough to consider the case where the group order was prime. And Shoup showed that an algorithm which can be used for general groups would require at least order root n steps. The birthday paradox idea suggests to us that root n should be good enough for this. There are order root n algorithms for discrete log, like Schenk's little step, big step algorithm, but that requires a lot of memory. As far as the Pollard Rho algorithm goes, the first result that I'm aware of was from Miller and Venkatasan a few years ago. And they showed that the random walk, which, yeah?
If you want the partition to be random, then you need a lot of memory as well.
So I was going to get to that on the next slide, yeah. Yeah, so I'm kind of glossing over a fact here. So if we just consider the random walk here, then that converges in order log cubed n steps. And this can be used to show that the discrete log is found in order root n log cubed n steps. And they've also shown, in some personal communications, they showed us that if you start from a random state, then almost always you'll actually find the discrete log. You won't get a degenerate situation. In a paper last year, we improved the mixing time result and slightly improved the analysis, and ended up getting almost down to the order root n steps that is predicted by all the people in computer science or by the birthday paradox idea. And in what I'm talking about today, we get it down to the right order. So basically a slightly bigger constant, but root n steps. And if we combine that with Miller and Venkatasan's result, then it should be non-degenerate. So now we get to what was being mentioned. So the previous idea behind this algorithm was that if we do this thing that looks like a random walk for a while, then we should be picking random group elements. And if we go root n times, then we pick something like root n random elements, and the birthday paradox says that two of them should be the same. But this ignores the fact that you have dependencies between all of these. So if we look at the state after 100 steps and 101, they're highly related. In our analysis, we make one assumption, which was referred to, that we're assuming that we really had a random partition. To actually store a random partition, we would have to store order n bits. So that would defeat the purpose of the Pollard Rho algorithm, that it involves very little memory. But it seems likely that if we work with some hash function that looks fairly random, that probably the analysis is roughly correct. But we don't have a proof for any specific example of that. So we'll make the assumption that we really have a random partition and claim that that's at least a lot better than the previous heuristic, and it seems likely that it should be fair. Okay, so let's get to how the proof works. To do that, let me refresh your memory about the birthday paradox, or the birthday problem. In the birthday problem, we have a bunch of objects. We keep picking with repetition, uniformly at random, and after about root n selections, we should have picked the same thing twice. The classic example is birthdays, and you have 365 or 366 of them. And once you pick between 20 and 30 birthdays, then you should have two of them that are the same. We can rewrite this as a Markov chain. Imagine that we have a complete graph, and at every step, we transition to any state equally likely. Well, this is really just the same thing that was just discussed. So that birthday problem tells us that after order root n steps, we'll eventually get back to some place that we've been before. And so one approach to improving on this, let's suppose that we've done our random walk long enough that where the chance of being at a state is at least half of what it should be, meaning half of uniform. In that case, we can prove the following result, which basically says that if we add an extra factor of square root of the mixing time, then we'll be able to get our birthday problem. And if we go back to the previous slide, if we're doing a walk on the complete graph, and the mixing time is 1 step. So this hasn't made things any worse. But the problem here is that most random walks have a mixing time which is not a constant. So we can improve on that. If we go a little bit further and go to the point where our distribution is within a factor of 2 of being uniform, then we replace the mixing time by some extra term there. And this extra term we refer to as the premixing, and this is the number of times that 2 independent walks would cross each other if they started at the same state. So we take 2 walks, we pick some state in our state space, we run both of these walks for the mixing time and count how many times they intersected, and the worst case expected value of that is the extra term going in here. So we would presume that if our random walk sort of spreads out very well, then these 2 walks probably won't intersect with each other very much. But if the random walk tends to proceed along a certain course, then the two independent walks might be crisscrossing each other quite a bit. So just a slightly improved version. So how do we apply this to the Pollard Rho problem? Instead of looking at the row walk, which you recall was add 1 to the first coordinate, add 1 to the second, or double, we're going to look at what we call the block walk. And in this walk, we just do the row walk, and once we do a doubling step, we stop. And we call that 1 step of our block walk. So on average, this would be three row steps, because you have probability 1/3 of making a Pollard Rho step a doubling step at each step of the algorithm. And we can show that after log squared n steps, this block walk converges. So if we think back to the,
I didn't understand what's the block walk.
Oh, the block walk is, so the row walk was that each step we either increment the first coordinate or the second, or we double. The block walk is do the row walk until you double.
Okay.
And that'll be called 1 step. So the number of row steps involved is a random variable, but on the expected value should be 3. On average, it takes about 3. That's fine here because we're only interested in the number of steps until the Markov chain crosses its previous path. And so if we only look at some selection of the states that it visited, then that's also just a pessimistic estimate. So the other term that was involved in our birthday paradox problem was this premixing term, the number of times that these 2 independent walks would crisscross each other. And we can show that it's related to this summation here. And the important thing is that if the probability of being at any state drops off by an exponential factor, then this summation will be a constant. And in particular, that's what we show here, that early on the Pollard Rho walk, the probability of being at any state drops by a factor of 2/3 at every step. And so then this term up here just ends up adding up to 18. And so if we were to go back to the theorem that we had earlier, we had the square root of the size of the state space times this premixing term of 18. And so that tells us that after 24 square root of n of these block steps, our block walk will have crossed a previously visited state. And every block step took on average 3 row steps, so that means that the Pollard Rho walk, after 72 root n steps, should have visited a state that it's been to before. And if we go back and we refine the constants a little bit, we can decrease that a little, but it's not really a big issue. The point was just to get root n. So that's what we can get. And so what were the main steps of this proof? The first thing that we had was our birthday paradox. And the way this was shown was by a second moment type argument. Instead of counting the number of times that the Markov chain crosses itself, we're just going to be concerned with intersections that occur reasonably far apart. That's what this term S is. So the times where the walk crosses itself that's separated by twice the mixing time. And then we use a standard second moment theorem to lower bound the probability that this is positive. And once S is positive, that means that our walk has crossed a previously visited state, and we've got our birthday thing. The mixing time component can be shown in several different ways. We can use canonical paths, we can use strong stationary times, we can use Fourier transforms, and Miller and Venkatasan's original result was using quadratic forms and characters. And any of these is sufficient because all we were concerned about was this premixing term AT, and that was fairly independent of what the mixing time was. So as long as the mixing time is around √n or below, then everything's fine. And the final step that we had to show was that the random walk diffused very quickly early on, so that there weren't many intersections of two independent copies of the walk. And this was shown by modifying the steps in a strong stationary time. So in the remaining time, I was thinking of which of these is more appropriate to cover, and since most of the talks seem to be on mixing times, I thought I would talk about that. And so several approaches can be used to mixing time here. The one that might be the most general, meaning applied to other problems as well, was based on using canonical paths. And generally the canonical path method is used for random walks that are lazy, meaning that half the time they do nothing and half the time they take a step. Diaconis and Slavkost, or maybe Struck as well, showed that if it's reversible, you don't need to assume it's lazy. But in this case, we have a random walk which is neither lazy nor reversible. So instead, what we do is combine a few previous results. So Phil, building on some work of Mihail, showed that the mixing time, the time for a random walk to converge to a stationary distribution, can be upper bounded by using the inverse spectral gap of P star. And P star here is the reversed walk. So that means take a step of the random walk and then take a step going back in reverse, and find the spectral gap of that. More formally, the definition is written down there. And as I said, if it's lazy, this is related to the spectral gap of the Markov chain you're actually looking at, and that's the version that most people use. Then several other authors have shown relations between the spectral gap and what are called canonical paths. And the idea here is that for every pair of states in our state space, we make a path connecting them using edges of the Markov chain. And as long as not too many of these paths pass through a single edge, then you can show that the spectral gap is fairly large. And by the previous theorem there, it follows that the mixing time is fairly low. But instead, since we don't have a lazy case, here we're going to have to combine these two, and we'll use the canonical paths, but instead of using edges of the Markov chain, we'll use edges of the Markov chain PP star. So a single edge is now a forward edge and a backward edge combined. And this isn't really relevant. We don't use this version of things, but I thought I'd refer to, Phil mentioned a Diaconis Phil paper before on duality, or he called intertwining. And it actually is possible to come up with another version of this, which is sometimes better, using evolving sets, which is a consequence that Morris and Perez showed of, well, it turns out to be a consequence of the Diaconis Phil result, but at the time they didn't seem to be aware of that. Okay, so just to remind people of how the canonical path result works, we have the paths using edges of PP star here. We have a quantity that measures congestion. This measures how many paths go through an edge. And in this case, our edges, though, were edges of the forward and then backward walk. And then we have a mixing time bound. It says that if we go enough steps, then this distribution that we have will be very close to what it should be asymptotically. And in this case, the distribution we're looking for is uniform. So it means that we have a nearly uniform distribution. Okay, so how do we do that? Now we're having to use this forward and backward procedure for our edges. If we just were to look at edges where we did a block step forward and a block step back, we would have a bit of a problem here, because the block steps ended by doubling, and so the reversed ones would start by taking a half. And so most of the time you're going to end up either near your initial state that you started at, because you might have done, say, +1 and double, and then a half, and maybe minus a few. Or you might end up with the plus k, where k was the, I guess I should have used x here, the discrete log that you're looking for. But the point is that if the value of k, or x, whatever we call it, is fairly small, in order to make a path that gets to the opposite side of your cycle, in this case, you would need to do quite a few, have very long steps. So instead, we're going to look at something slightly different. We're going to look at a walk which most of the time does a single transition, but sometimes does two of them. And people might complain this is not a mixing time anymore because the number of steps that we're considering here is now a random variable. But that's not a problem because we weren't really concerned with mixing time all that much. We were just concerned with the expected number of steps until the walk crosses itself. But I'll get back to the mixing time problem in a minute anyways. So if we looked at this other version of things, what's nice is that we can construct steps which go from a state to twice the state, or from the state to twice plus 1. And this will be useful because we can end up using a binary expansion of a difference between states in order to find nice short paths. If we were actually looking at the Pollard Rho walk, we would have a similar problem that just going forward and backwards wouldn't be good enough for us to find short paths. But instead, if we looked at doing 2 steps forward and 2 steps back, then you can actually make things work, and you get a similar property that you can make steps where you go from the starting point to twice that, or twice that minus 1. So in that case, we really would be looking at the mixing time of our original row walk. But for our analysis, we want something related to this block stuff. Okay, so the length of the paths that we'll construct will be log n, where n was the group. And if you recall, what we're really doing here in this row walk is a random walk on a cycle. So we're doing a random walk where we either move to the next state, or we move plus x, or we double the position. And we'll make the pass by taking the difference between the destination v and 2 to the n times the starting state. The reason for that being that if we do n steps, we'll have doubled n times. And so the starting state will have effectively moved to 2 to the n times where it was. And then we can use the binary expansion to come up with a path somehow. And then we can measure our congestion and reach a conclusion about the mixing time. And in this case, the canonical path method doesn't give the best result, but that doesn't really matter for us. So the Fourier analysis method will give a better result, but that seems more specialized. Seems like there might be other non-reversible, non-lazy Markov chains where this idea might prove useful. So that's why I thought it was a good one to finish with. And so if you're interested in finding out more details, like the proof of the birthday paradox part or the pre-mixing bit, then you can look at the paper, and it's also on arXiv as well. Okay.
Can I ask
Yeah.
something? So you're bound for non-reversible chains that pi mean in the denominator?
So you're saying this pi x pp star, is that what
Yes,
you're saying?
yes, yes.
So in this case, in the Pollard
No,
Rho
I know,
walk,
in this case it's okay.
Yeah.
But for general non-reversible, it's not
Mhm.
okay, right?
pardon?
For general non-reversible, it's not okay because pi mean can get really small.
Yeah, so in general non-reversible, if that denominator is very small, it might be better to use this theorem, which I mentioned here, which is using the Diaconus and Phil stuff. So this theorem of mine in the denominator only has the minimum of pi x times p. So it looks like the regular canonical path theorem.
Yeah, I understand it.
Okay.
It's, yeah. Okay. Thank you.
And let's thank the speaker again.